Now we move on to piece of f. Piece of f is our structure fixed force vector. It is in the location and position of the degrees of freedom, so which means that the number of piece of f is equivalent to the number of degrees of freedom. So how are we going to solve for piece of f? How are we going to identify? So to identify this one, you have to compute first, find the value for q's of f, our member fixed end forces for every member. For example, you have 3 members in the beam, which means that you're going to have 3 q's of f. For this example, you have 3 members, so you have here f sub f q's of f1, q's of f2, and q's of f sub 3. So which means that for every member, you're going to identify the member fixed end forces. So the formula that you will be using are the formulas that was presented a while ago in the computation for our member fixed end forces. Once you have the identified value for our q's of f for member 1, member 2, and member 3, you have to write now the code numbers. So the code numbers that we have identified a while ago for every member. So you have to write that on the side. So actually, these are the numbers of your restraint coordinates and degrees of freedom. So a while ago for our S, we also have our code numbers. Actually, those are also the value for our code numbers for our member fixed end forces for that will be written on the side. Once you have now the value, the code numbers, you're ready to assemble your piece of F. So how to assemble the piece of F? So which means to assemble our piece of F, we have to identify the number of degrees of freedom because it is in the location and position of the degrees of freedoms, which means that the number of piece of f is equivalent to the number of the degrees of freedom. So for example, there are in our illustration there will be there are 3 degrees of freedom. So this is the illustration. For example, you have here piece of f1, piece of f2, and piece of f sub 3. So this is in the location and position of our degrees of freedom. So which means that we have 3 piece of f. So we're going to have here, you have to write on the side in matrix form. Of course, you have to fill in this elements in matrix form. So piece of f actually, so you're going to have, if you're going to write that one, so you will have piece of f is equal to, in matrix form, you have to write the number of degrees of freedom. So 1, or the number of degrees of freedom, which is equivalent to the number of piece of f. So that is 1, 2, 3. Then how are going to have this value? How do we have now this value? So that value refers now to the code number that has 1. So you go back to q's of f1 for member 1. So identify if there is a code number 1. So there is. Then there is a code for member 2. Yes, there is. Then code member 3, there is none. So you have to plus member 1 and member 2, the value to that. Then we have the next one is code number 2. So member 1, mayroon, there is, rather, then member 2, there is, then member 3, there is none. So you have to add this 2 value for our q's of f. So that will be member 1 and member 2. Then for our 3, for our code number 3, so we have here member 1 doesn't have, member 2 there is, and member 3. So you have to add the value for code number that belongs to code number 3 for member 2 and member 3. Then you simplify that one. Then once you simplify, you have now the value. For example, the value as you simplify would be 4, 3, and -1. So this is now the value for your structure fixed force vector or piece of F for that particular structure, or we are referring to the beam. Then we have what we call equivalent joint load vector, which is denoted by P sub E. And that P sub E actually is the negative of the fixed joint force vector. So which means that P sub E is equivalent to the negative value of our P sub F. So that is now the value for our equivalent joint vector. So we have here an example. Determine the fixed joint force vector and the equivalent joint load vector for the prop cantilever beam. So for this one, fixed joint force vector, our P sub F and P sub V, we have to identify that one. So to solve here, we have to identify first our Q's of F1 and Q's of F2. Since we have 2 members here, we have we're going to have here 2 members since the material for this is not uniform all throughout the beam. So we have here, we can have this member 1, and we have here, this can be referred as member 1, and you have here your you have the other one as member 2. So this can be member 1 and this is member 2. So therefore, you have to identify first the member fixed and forces or Q's of F for member 1 and Q sub F is also for member 2. So for member 1, of course, this is uniform loading. So you make use of the formula for a uniform loading to have the value for shear forces and moment forces. And if we're going to substitute the value to our variables in the equation, we obtained 135 kilonewton to 0.5 kilonewton meter and negative to 0.5 kilonewton meter respectively. And if you're going to write that in matrix form, you have now the value. So you have now the value for our Q's of F1. And we try to identify our code number here for member 1. For member 1, if you're going to have the value of code value, so we have identified here our degrees of freedom and the restraint coordinates for our beam. So at member 1, of course, fixed, there is no degrees of freedom. At member 2, at joint 2 rather, there is a free joint, so you have 2 degrees of freedom, translation along y direction, and rotation. So you have 1 and 2. So you have to number first translation followed by rotation. At joint 3, this is a roller, so there is rotation. So you number that as 3. Then going back to joint 1, you have a restraint coordinates, so it will start at 4, then followed by 5. Then, of course, at member 3, there is also a restraint coordinate, which has along y direction for translation, so that is numbered as 6. So now, for member 1, if we're going, since we have computed now our Q's of F, we have computed now our Q's of F1, our member fixed and forces. So we have also identified our code numbers. So the code numbers here, so for member 1, you have 4, 5 at the beginning of the member and 1 and 2 at the end of the member. So we have here 4, 5, 1, and 2 at the beginning and at the end of the member. Then, if we're going to identify now your value for member 2 for Q sub F for member 2, so same procedure again, use the formula for uniform loading for the shear forces and moment forces. So we have here identified 105 for both for the beginning and end of the member for the shear forces. Then we have 122.5 for the shear force at the beginning and for the moment force at the beginning and moment force at the end, which has negative 122.5. So if you write that in matrix form, you have now the value for our Q sub F2. This is the member fixed and forces for member 2. And if we're going to identify the code numbers for member 2, if this is member 2, the code numbers will be at the beginning is 1 and 2, then 3 and 6. So you have here the values 1 and 2, 3 and 6. So you have now the value for your Q sub F2. Now after that, you could identify now the value for our piece of F. So for the piece of F, for the structure, we're going to have assemble our structure, the value for our structure fixed force vector. So the value for our structure fixed force vector, fixed joint force vector is, which is our piece of F. Since there are 3, if we're going to observe, there are 3 degrees of freedom, so which means that there are 3 also piece of F. So 1, 2, and 3. So since there are 3, so you have to write down here. So we have here our value, which has code numbers. So 1, 2, 3 to represent that there are 3 piece of F since there are 3 degrees of freedom. So how to obtain this one? So you go back to member 1, Q sub F1. If there is a code, if there is a code number, so there is 1, so you write down 135. Member 2, there is 1, so you add that one. So which means that 135 plus 105, so you get here 240. So that's the result. Then at for code number 2, the next one, code number 2, we have here member 1, there is negative 202. Then member 2 is negative 122. So we have here the values. So you can have the value which is equivalent to equivalent to this specific value. So you simply have to write that one. Then for 3. For 3, there is also a value. For member 1, there is no code number 3. For member 2, there is code number 3. So you have to write that one. So which means that for our result, you have now the result. So you have 240, negative 80, and negative 122.5. So this is now the value for our piece of f, our structure fixed joint force vector. So if we're going to observe, they have a specific, do you have other values for piece of f for each member? So what the solution here, they try to obtain the value for piece of f for each member. However, you can have another solution wherein you can immediately get the value for piece of f using q's of f. So once you have the q's of f for member 1, member 2, you could identify immediately the value for structure fixed joint force vector, your piece of f. Then afterwards, once you have now the value for piece of f, you could identify now the equivalent joint load vector. So the equivalent joint load vector, piece of E, will be equivalent as the negative of your structure fixed joint force, or piece of E is equivalent to negative piece of F. So you simply have to get the negative value we have here, which means the negative of piece of F. So you multiply your value for piece of F by negative. So once you multiply that one, so this would result to negative 240, this one would result to positive 80, and this one will result to positive 122.5. So you have now the value for structure fixed joint force vector and your equivalent joint load vector.